Okay, so let's start. So last time we were talking about limits at infinity. Now, just to remind you, so the definition is now a little bit different to the previous definition. So we now consider the limit of a given function as x tends to infinity. This is the difference, because previously we just looked at the situation where x approaches some number, and the meaning of this symbol again is that, okay, for all epsilon larger than 0, now I can find some m which might depend on epsilon, so some index or some large number, such that if x is larger than this m, then the distance between f of x and L is smaller or equal than epsilon. So the only difference in the epsilon delta definition is here, because if you have a number a, you have to find a delta such that if x is close to this number a, then f of x and the distance of f of x and L has to be close enough. Now the only difference is we assume that it has to be large. And similar if we define the limit of f of x as x tends to minus infinity. So we have the same definition. Now, we saw already last time some examples. Of course, you know this already from high school. You know how to treat those examples from high school. The only difference here is that we start from this definition. Then we first use the definition to prove the limit laws. I haven't done this. I told you that all the limit laws for the case where x approaches some real numbers hold in this situation as well. And then we figure out limits of some simple functions like 1 over x and so on using the definition. And the rest is just building from the simple functions and the limit laws. So just to demonstrate this once more, let's look at another example, an easy one. So if we consider the function square root of 9x squared plus x minus 3x. Now just to see once more how this building works from the limit laws and from easy functions. But of course you know this from high school. So if we want to figure out the limit of f of x as x tends to infinity, now of this expression, okay, so the main thing is we cannot immediately use the limit laws. We cannot use that the limit of a difference is the difference of the limit, because those two limits do not exist. And the limit laws have an assumption that the limits, all involved limits, must exist. So we have to use a trick here, and this trick you have already learned in high school, namely you multiply you multiply this function with the square root of 9x squared plus x plus 3x and divide it by this expression. So you have the function 9x squared plus x minus 3x, and then you multiply with the square root of 9x squared plus x plus 3x over the square root of 9x squared plus x plus 3x. Now we haven't changed anything. But this here makes a considerable difference, because if you compute this, then you see, okay, this is x here over, and then you have the square root of 9x squared plus x plus 3x. Also, this is not helpful, because if you try to use the limit law for a limit of a quotient, you cannot do it as well, because this tends to infinity and this tends to infinity. So the limit do not exist. So you need, again, another trick here. And of course, you know what the trick is. You multiply numerator and denominator both by 1 over x. So you should understand this. The multiplying here is in order to make the limit laws work. Okay. So you have here 1 over. Now, we want to take 1 over x inside the square root, because x is positive. We can just take it inside and have 1 over x squared. We do not have to care about the sign. And we get 9 plus 1 over x plus 3, and now you can let x, now you can use the limit laws, finally, okay, and if you use now the limit laws, you see, okay, you get 1 over 6. Okay, so here you see that what I actually just used is, so these are some transformations in order to be able to apply the limit laws eventually. So I haven't done anything here or here. This is just, I just have changed the expression, the original expression, to this one here. And now here at this step, I can use the limit laws. And if I know that, I have to know that the limit of a fraction is the limit of the numerator over the limit of the denominator. I have to know that the limit of a sum is the sum of the limits. I have to know that the limit of a square root, I can take the limit under the square root. I have to know that the limit of a constant is the constant itself, and I have to know that the limit of 1 over x as x tends to infinity is equal to 0. So here you see all the basic steps which we prove first. And once we have done this, we can completely avoid using the definition and just have to apply the limit laws and what we already know. Okay, so what you should understand here is, of course, something like this you have done already in high school, but the important new thing is that we start from this definition, from the precise definition, and prove everything with the precise definition. Of course, you could try to use the definition directly onto this function. You can try to apply the definition directly to this function, but you will easily see that this is not so easy to find for every epsilon the right m. Okay, so here you see why it makes sense to first prove things for simple functions and then prove the limit laws. Okay, we avoid that we every time have to find the m for a given epsilon. Okay, so any questions to this? Now, we will see the same approach many, many times throughout this lecture. So whenever we have a complicated problem, like trying to figure out such limits, we will first prove for some simple functions what is the limit. We will prove some tools, how to handle sums, differences, and so on, and then we will start to build more and more complicated examples. Now, of course, you can also define infinite limits at infinity. You have a similar epsilon delta definition, or here epsilon m definition. Okay, so you can do it on your own. You can easily figure out what I mean by something like this here. It's plus or minus infinity. And you can also easily write down the precise definition of this here. Plus and minus infinity. So also for this here, we have a precise definition. So once more, maybe this does not mean that the limit exists. This just means that this actually means that the limit does not exist. But the limit does not exist here in a very special sense. Okay, namely, if x is getting larger and larger, f of x is also, if you have, for instance, plus infinity, is also getting larger and larger. Okay, this is what this symbol here means. So the limit does not exist, but in a very specific sense. And of course, as you know that if you look at some functions like x to the cube as x tends to infinity, then as x is getting larger and larger, x to the cube is getting larger and larger, and what you get is infinity. And similar for other power functions like limit x tends to infinity, x to the 4 is also equal to infinity. Also the limit x tends to infinity of e to the x is infinity. Okay, but actually, you see this symbol doesn't say anything about the speed of growth, okay? Because actually there is, of course, a difference between this function, and this function as x is getting large. Namely, this function is growing to infinity much faster than this one, and this one is growing even faster than this one, and so on, okay? So you have something like, okay, x to the 3. Sometimes in mathematics we use this symbol here to say that this function is much, much smaller as this one, as x tends to infinity. And actually, for every power where n is larger or equal than 5, you have something like this, and e to the x grows faster than any such power, okay? And then there is a function. Can you think about a function which even grows faster than e to the x? Yeah, x to the x grows, of course, much faster than e to the x. Then a function which grows slower than any power is, for instance, the logarithm of x. But of course, there are also functions which grow much slower than ln of x, for instance, the ln of x, and so on and so on. Okay, so you have kind of different types of growth. Okay, but those different type of growth you do not see from such a limit relation. Okay, we will later on prove precisely that this function grows faster than every power, and so on. Now, for infinite limits at infinity, because actually the limit relation tells you that the limit does not exist. Okay, of course you cannot apply the limit laws. Some of the limit laws still hold. Okay, if you interpret them suitable. Okay, so for instance, of course the limit of x tends to infinity of x plus the square root of x. Of course this is infinity because this function grows to infinity as x grows to infinity. Okay, and somehow you can write this as the limit of x as x tends to infinity plus the limit of square root of x as x tends to infinity, because infinity plus infinity is very large. Okay, it's infinity. Now, but of course you cannot use this if you have, for instance, differences, or if you replace this by the difference, then now you cannot say, okay, I write this as the limit of x minus the limit of the square root of x, and then I do not get anything from this. Okay. Because both are growing, okay, and you do not know. Eventually, it's kind of you do not know which one wins, okay, because it's like it depends which one is growing faster. Now, of course, in this case, it's easy to argue, okay. You just rewrite the function as square root of x times square root of x minus 1. Okay, now it's easy to argue because you know this as x gets large, this gets large, and this gets large as well. And if two functions are, if you have two large values, the product, of course, is large as well. Okay, so from this expression, you see actually that this is equal to infinity, and we are kind of using the limit laws. Okay, we kind of argue just with the two factors. Okay, but you cannot do this for this function. Okay, as you know, here you have something like here infinity minus infinity, and infinity minus infinity can be everything. Okay, depending on which. Because you can look at this as a function, and this is another function, and it depends which one is growing faster. Okay? So if you choose both functions to be equal, you get 0. If you choose here square root of x and here x, you get minus infinity, and so on. So you can get everything. You can construct just every number as a limit. You can find two functions such that you get any number as the limit. Okay? And also from this example, you see that once more, that for infinite limits at infinity, you cannot directly use. You have to be careful in using the limit laws. You are invited to write out the precise definition of such symbols and to prove such limit relations using the precise definition. You can try it on your own. Now, there is one example in our textbook. Let's maybe just stick to this example, because this is also... So you have given a function which is y is equal to x minus 2 to the fourth x plus y to the cube x minus y, x minus 1. Now find the intercept and limits as x tends to plus minus infinity. Of course, this is easy in this example, but just to explain, maybe you are not so familiar with the term intercepts. The intercepts are the points where a function intersects with the y-axis and the x-axis. Okay. Of course, they are important for understanding, okay, where is the function positive, where is the function negative. Now, in this case, you see that the so-called y-intercept okay, so those are the points where the function meets the y-axis. So you just plug in 0. Okay, so this is y of 0. Okay, so where you have 16 times 3 times, so minus 16. Okay, so this is the y-intercept, and there's only one. And the x-intercept are the points where the function intersects with the x-axis. Okay, so you have x is equal to 2, x is equal to minus 1, and x is equal to 1. Okay, you see that if x approaches 2 for this point here, because you have here 2d4s, okay, so the sign does not change of this function, and the limit of the function, maybe call it f of x. Okay, so the limit of the function as x tends to infinity. Now, you just see it from the factor. So actually, in this case, you can apply the limit laws. You see this tends to infinity, this tends to infinity, this tends to infinity, and the product of infinity is infinity. So you get here infinity. And the limit as x tends to minus infinity. Okay, so this tends to plus infinity, this tends to minus infinity, this tends to minus infinity as well. So everything tends to infinity. And now from this information, this is quite helpful because from this information you can already plot the graph. You already know quite a lot of properties of the graph. So you have here x, you have here y. Then we need the points 1, 2, minus 1. So you do not have any sign change at 2, and then you tend to you go to infinity. You have a sign change here. You have a sign change here, and for x getting small, you also tend to infinity. So it roughly looks like of course, certain properties we do not know yet. Okay. For instance, we do not know that at x is equal to 0, you have an absolute minimum. Okay. In some sense, okay, we have to argue a little bit more than just looking at the intercepts and the behavior as x tends to infinity and minus infinity. Okay, we will try later on. We will have quite a lot of tools how to figure out. Okay, where are those x where the function is getting small? Okay, locally small, and where are those x where the function is getting large, and so on. We do not care about this at the moment. The important thing is that the behavior of a function, okay, as x tends to infinity or x tends to minus infinity is quite important, okay, because of course you can use a graphing device to plot something like this, but if you use a graphing device, you always have to choose, okay, the range of which you plot the function. Now, from a graphing device, okay, just using a graphing device, you will never be able to understand. You just understand how the graph looks like locally, never globally, okay. But this here gives you the global behavior, okay. So the behavior as x tends to is getting large and small, something which is never captured by just using a graphing device in order to plot the function. That's why this information is quite important, and this is something a graphing device, like Maple, cannot give you just by plotting the function. Any questions to this? I guess this should still be quite similar to what you have learned in high school. It's just a little bit, we look at things a little bit more from a different angle, and we build things more systematic, starting from definitions. Now, actually, the reason why you define limits in high school is because you want to look at continuous functions. So this is the next topic. Okay, so you have learned this already in high school. I guess in high school you give the following definition. Okay, so f is called continuous at some point x0 if the limit of f of x as x tends to x0 is very easy to compute, namely is equal to f of x0. Okay, so this special situation, if this special situation occurs, and we saw already this special situation occurs for quite a lot of functions, namely polynomials, rational functions, and so on. If you have this special situation, then the function is called continuous. Maybe in I do not know whether in high school you start from this definition or you just say that if you plot the graph, you can draw the graph without lifting your pencil, okay, just in one line. So this is, of course, this is not a very good definition, okay. I guess most of you have seen this definition in high school. If a function is not, if this does not hold, if a function is not continuous at x0, it's called discontinuous at x0, and x0 is called the discontinuity of the function. Okay, so if f is not continuous at x0, it is called discontinuous at x0, and x0 is called discontinuity of f of x. Okay, so this is just terminology. You should memorize it. Now, I just want to stress that actually this definition contains 3 requirements. Okay, the first requirement is that the function is defined at x0. This is something which is not which you do not necessarily need to have if you look at such limit relation. We saw many functions where actually the function is not defined at x0. So here the first thing is the function must be defined at x0. Otherwise you cannot evaluate this. The second is the limit must exist. And the third is the limit is equal to f of x0. So you have 3 requirements. Okay, so the first one, f is defined at x0. The second, the limit of f of x as x tends to x0 exists. And the third, the limit of f of x as x tends to x0 is equal to f of x0. So you need three requirements. That in order a function to be continuous at the point x0, the function is defined, the limit exists, and the limit is equal to f of x0. 3 requirements. So let's maybe look at cases where the function is not continuous. You have seen already many functions in high school which are continuous. So let's maybe first just discuss the case where the function is not continuous. In particular, let's look at the examples where maybe the first does not hold, the first holds, but the second does not hold, the first and the second hold, but the third does not hold, and so on and so forth. So for instance, let's look at a couple of examples. Okay, so let's maybe look at the first example. F of x is equal to x squared minus 1 over x minus 1. x0 is equal to 1. Second example, let's look at f of x is equal to, let's for instance look at 1 over 1 minus 2 to the 1 over x. And let's this define as 0. So if x is not equal to 0, if x is equal to 0, the point we are interested in is 0. Let's look at f of x is equal to 1 over x if x is not equal to 0 and 0, if x is equal to 0. And let's look at f of x is equal to, let's say, x squared minus 1 over x minus 1 if x is not equal to 1, and let's say 0 if x is equal to 1 and the point x0 is equal to 1. Okay, so for all those examples, okay, you see, we are interested in this point here, okay. So for this, the first example is of course not continuous at this point because the function is not defined at this point, okay. So this function does not meet the first requirement, okay. Now, for this function here, we do not have the problem that the function is not defined, okay, because the function is defined, okay. So we have to check now whether the limit exists, okay. But here in this case, we know that, so for 2, here the limit of f of x as x tends to 0, let's say from the right. So here, this function 1 over x is getting larger and larger. 2 to a large power is getting larger and larger. So what you get is 0. And the limit as x tends to 0 from the left is, now this is getting smaller and smaller. So this tends to 0. So everything is tends to 1. Okay. So from this we see that the limit does not exist. Okay. So also this function, we know already now, is not continuous at 0 because it doesn't meet the second requirement. The first requirement is satisfied, but not the second one. Okay. Now, for this function, okay, as x tends to 0, again, if you come from the right, it tends to plus infinity. If you come from the left to minus infinity, okay, it doesn't exist. Okay. So for the limit, for instance, of f of x as x tends to 0 from the right is plus infinity. So from this, you already know that the limit of f of x as x tends to 0 from the right does not exist. So actually, this function is, I didn't say what is the x0 is. x0 is 0. So actually, for this function here, okay, the behavior is the same as this one. Okay, the first requirement is satisfied, but the second requirement, okay, is not satisfied, okay. But actually, the way the second requirement is not satisfied is a little bit different because this function here jumps at 0, and this function tends to infinity, okay. So the behavior is different. And now finally, for this function, you see the first requirement is satisfied, namely the function is defined at 1, so no problem. Now the second requirement, if we look at the limit of f of x as x tends to 1, okay, so this is the limit of, the function now becomes x plus 1. Okay, so because you can write this as x minus 1 times x plus 1, you can erase x minus 1. And now, this is now a polynomial, so for this one we know that this is equal to 2. But 2 is not equal to f of 0. Okay, so here the third requirement is not satisfied. The first and the second are satisfied, but not the third one. So also here, f is not continuous. Okay, so you have seen here, you should, of course, all those examples are easy examples. Okay. But you should recognize that the way they fail to be continuous is different, okay? The first one was not defined at x0. The second and third one, the limit did not exist, but they were defined actually at x0. The third one is defined at 1 at x0, the limit exists, but it's not equal to the function value. So they are all kind of different. Okay. Now those two are kind of similar, but the behavior, the way they fail to be continuous is different. So if you plot the graph, this one, we tend to 0. Sorry, we can say, okay, of course we do not know here. Of course it would be easy to figure out whether the function is positive or negative, but we don't have to do this. So this point is included. Now we have something here at 1. Okay, so locally the function looks like this here. So you see that the function jumps here. And so this is the second example. And for the third example, okay, so this is the third example. So in both cases, the function is defined at 0, but the limit does not exist. Now, there are different names for such discontinuities. Okay, this is called a jump discontinuity, and this is called an infinite discontinuity. Okay, so maybe this is terminology. So this is called a jump discontinuity. And this is called the infinite. Okay, so in those two cases, if the function jumps at some point, okay, or tends to infinity, okay, in some direction, okay, there is no hope for the function to repair it at the point such that it gets continuous, okay, because the limit does not exist, so you cannot do anything. Okay, but in the first and second, in the first and fourth example, see, they are quite similar because it's the same function, except that x is equal to 1, where the function is defined differently. So in those cases, for first and 4, so this is 4 here. Okay, so if we define a new function, let's say g of x. Okay, so the same function x squared minus 1 over x minus 1 if x is not equal to 1, but 2 if x is equal to 1. Now, because we computed the limit here, we know that the limit is equal to 2, so now the function is continuous. Okay, so in the first and fourth example, you can repair the function. You can change function values such that the function becomes continuous. Okay, such a situation is called, such a discontinuity is called removable. Whereas in the second and third case, okay, because the limit does not exist, so the discontinuity cannot be removed. The function cannot be repaired such that it gets continuous. Okay, so they're kind of a very different behavior. Okay, and essentially these are the important behaviors. So you have a jump discontinuity, or you have an infinite discontinuity, or you have a removable discontinuity. Okay. Only in case where you have a removable discontinuity, you can remove it, as the name already tells you. Okay, any questions to this? So this already classifies, okay, the ways a function can fail to be continuous. Now, let's maybe look at a more interesting example. We have already seen this example here, which is kind of our toy example. Okay, we have already seen that that the limit of f of x as x tends to a does not exist for all a not equal to 0. Okay, so in this case, the function cannot be continuous. Okay, so the function cannot be continuous for all a which are not equal to 0. And we have seen that the limit of f of x as x tends to 0, okay, is equal to 0. Just to remind you, we use the squeezing theorem. It's the most easiest way to see this. Okay, but 0 you see is f of 0. Okay, so you see actually this function is continuous just in one point, namely 0. Okay, if you plot the graph is something like you have something like x squared, okay, but it's dotted, and on the x-axis you have also many points, okay. Now, if you just use this primitive definition of continuous, namely a function is continuous if you can draw the graph, okay, without lifting the pencil, okay, it's kind of, it doesn't really work for such a function, okay, to figure out that this function is continuous at 0, which is actually the case. Now, maybe in high school you have seen this. We have already discussed this example several times. Maybe you have seen another example which is slightly more interesting. Zero. And here, I think I haven't mentioned this yet, so you have P over Q. Then the greatest common divisor. You know what the greatest common divisor is? Everyone knows. The greatest common divisor of 3 and 6 is 3. It's the greatest number, the largest number which divides both numbers. Okay, so the greatest common divisor of P and Q is equal to 1. In other words, this fraction is reduced. Okay, and here you define the. Now, how about this function? Where is this function continuous? This example, maybe you have seen it in high school. This is a famous example due to Riemann. I give you a little bit time to think about it, discuss with your neighbor, and then we discuss it. So take a little bit time to discuss, in case you do not know the example. If you know already the example, then this here. Of course, this is not 9, okay? This is Q, okay? This is this Q here, the denominator. If it would be 9, the answer would be trivial. Function is nowhere continuous if it would be 9. Maybe let's look first at the case. So actually the function is everywhere defined, okay? It's no problem, okay? So this is the first thing. So the function is defined everywhere. For instance, at 0, okay, what is the function value at 0? 0, if you want to write it like this, you have to write it as 0 over 1, okay? Actually, I forgot something. Sorry, Q must be larger than 0, okay? Because you have already, also for negative, you have a sign here, and sign goes to P, okay? This is also important. Now, if x is equal to 0, okay, what is the function value? The function value is equal to 1, okay? Because 0 you can write as 0 over 1, and the greatest common divisor of 0 and 1 is 1, okay? So the function value of 0 is equal to 1, okay? Now, if a is any rational number, okay, so the function is defined everywhere, okay? So the function certainly meets the first requirement, okay? Now, we have to figure out limits, whether limits exist or not. Okay, this is the second requirement. If a is a rational number, okay, does this limit exist or not? Yes or no? If you think about the point x is equal to 0, okay. So here the function value is 1, okay? But close to x is equal to 0, you certainly have also many irrational numbers where the function value is 0, okay? So kind of at 0, the function kind of jumps, okay, to 1. Okay. So you have that this limit does not exist. Actually, for all a in Q, okay, because once more, if you have something like this here, okay, if you have any rational number, okay, you know from this definition that the function value is some positive number, okay, maybe very small, but positive, okay. So the function value is some positive number, okay. But you know if you are close to a, there are always irrational numbers, okay, which are mapped to 0, okay. So it's certainly for a rational number, okay, it's possible to find a small epsilon such that no matter how small you make delta, okay, there are always function values inside the delta interval which are mapped outside the epsilon strip, okay. So, or differently, you can kind of say, okay, the function jumps to this point at a is equal to q, because if you leave a little bit, you will immediately find an irrational number where the function value is 0, okay. So this limit does not exist, okay. So the function is certainly not continuous for rational numbers, okay. So this is not very different from the homework example where you have 0 and 1, okay. You use the same reasoning, okay, for rational numbers. Now, the more interesting case are irrational numbers. So now a is irrational. Now this is a little bit more tricky. So here the limit, I claim it's equal to 0, okay? And 0 is also f of a, okay? So in this case, the function is continuous. So this is an example of a function which is continuous for all irrational numbers, but discontinuous for all rational numbers, okay? It's kind of very strange behavior. Now, how to argue here in this case? Okay, you do not have to use the epsilon delta definition. Just a rough argument is enough. Now, our a is an irrational number. Okay, so here for an irrational number is mapped to 0. Okay. Now, what you do is you give an epsilon strip. Okay. The question is, can you find the delta such that if you choose the delta small enough, okay, all those x here have a function value which is inside the epsilon strip. Okay. Now, of course, this interval here contains both rational and irrational numbers. Okay. Now, for the irrational numbers, you do not have a problem because the function value is 0. But for the rational numbers, you have a problem because the function value might be outside the epsilon strip. Okay. Now, if a is an irrational number and you make this sufficiently small, okay, of course you will encounter rational numbers, but the rational numbers will have a large q, okay, which means that 1 over q is getting small. So they are mapped inside the epsilon strip from some point on. Okay. So you can choose a delta interval which is small enough such that all the x have a function value inside the epsilon strip. And this proves by the epsilon delta definition of the limit that this limit is 0. Okay. Of course, this is not a precise proof. This is just, I just argue here. Okay. But so the important property you need is if you make the interval small enough, if you consider a small enough interval, okay, of course in this interval you will always have, no matter how small delta is, you will always have rational numbers. Okay. But the important thing is that those rational numbers will, if you make this sufficiently small, will have a large q, okay, which means the function value is small. Okay, so this example maybe is not so easy to understand, but this gives you another example which tells you that the most easiest definition of a continuous function, namely a continuous function is a function where you can draw the graph without lifting the pencil, is not useful, okay? Because obviously you cannot apply this This definition does not tell you anything whether this function is continuous or not, okay? And this function has a pretty strange behavior. Because if you think about this function is, for all irrational numbers, the function is continuous. But for all rational numbers, the function is not continuous. Any questions? It's not necessary that you completely understand this. If you didn't get my arguments, maybe sit down at home and try to think about it once more, and you will figure it out maybe on your own. Now, you see, this example here is quite special in the sense that if you look at the continuous property just from one direction, okay, so if you look here at the continuous property just from the right, this function would be continuous, okay? So if you replace the original definition by the right, if you replace in the original definition the limit by the right-hand limit, okay, then this function would become continuous, and this is called right continuous. So this function is right continuous, okay, but not continuous. So we have also the following definition. F of x is called right continuous at x0 if the limit of f of x as x tends to x0 from the right is equal to f of x0. Okay. So you see that because if you just look at the right-hand limit here from this side, you see the function is also continuous at 0. So the function is continuous everywhere. If continuous is now right continuous, so this function is right continuous everywhere. Okay. And similar, you have a definition for left continuous. So f of x is called left continuous at x0 if the limit of f of x as x tends to x0 from the left is equal to f of x0. Okay. And the function is continuous at x0 if and only if it is right continuous at x0 and it is left continuous at x0. Okay. So this is kind of a tool which helps you for more easily for some function to decide where are they continuous. So maybe you have seen this definition already in high school as well. What is the time? Because we do not hear. Okay, so let's make a break of 10 minutes and then let's go on at 11:10. We just introduced the concept of right and left continuous. This is, of course, similar to right-hand limit and left-hand limit, and it has also the same. The reason why we introduced this is the same as the reason why we introduced right and left-hand limit, which is it's just a convenient tool to figure out or to argue that the function is not continuous. Namely, if you compute the right, for instance, like this here, this function is right continuous but not left continuous at the point 0, so it's not continuous. Okay, so it's a convenient way to argue. Now, the next definition you find in our textbook is f is called continuous some interval if f is continuous for all x in the interval. Okay, so here this is continuous on an interval. Okay, so if we say a function is continuous on an interval, we mean that the function is continuous everywhere inside the interval. Now you have here two boundary points, a and b. Okay, normally if you have something like this here, we assume that if you have a point inside the interval, okay, we use the usual definition of continuous, and for the boundary points we use either left or right continuous. Okay? So we assume here that the function is continuous for all x inside the interval, and for x is equal to a, the function has to be right continuous, and for x is equal to b, the function has to be left continuous. Okay? We always assume this if we say continuous on an interval. Okay? Maybe also pay a little bit attention to this here. We say on an interval, not at an interval, but we say at a point. Okay? So pay a little bit attention to these wordings. Now, so for instance, in our textbook, you find the example. One minus. Okay, so you see that the domain is minus 1, 1, and it's easy to figure out with our limit laws that this function here is indeed continuous at this interval. Okay, it's also no problem for the boundary points because our limit laws also hold for left-hand limit and right-hand limit. Okay, so you can just use our limit laws here to figure this out. And now, what is following next in our textbook is actually just translating, because it would be too complicated, okay, or too tedious every time to go back to the definition of continuous in order to argue that the function is continuous. Okay, so we just do the same as for limits. We first figure out that certain functions are continuous and that we have certain rules for building functions which preserve the property of being continuous. For instance, if you have a function which is continuous, if you have two functions which are both continuous, then the sum of the functions will be continuous as well. Okay. Now, of course, this follows from the limit laws. Okay. So if you have two functions which are continuous at a, then also f and g which are continuous at a, then also f plus g, f minus g, f times g, f divided by g, if g of a is not equal to 0, will all be continuous at a. Okay, so you have such certain rules for building. Okay, and we already saw that all polynomial functions and all rational functions are continuous on their domain. Okay. Okay, so all polynomials and rational functions are continuous on their domain. You should understand where this is coming from, okay? This that the polynomial is continuous, okay, does not come from the fact that we look at the graph, okay, and the graph looks like it's continuous. Okay? We do not use such a way of arguing, okay? So actually what is behind here is just the limit laws, okay? We first figure out that the function, we know that the function f of x is equal to x is continuous everywhere. This is one of the limit laws. We know that a constant function is continuous everywhere. Again, this is one of the limit laws. And then we know that sums of continuous functions are continuous. We know that products of continuous functions are continuous. We know that if you multiply a continuous function with a factor, you get a continuous function, and so on. And using such rules, you can build this theorem. Okay. Also, this is also helpful for like if you have a function like f of x is equal to the absolute value of x. Okay, because you know already that for x negative, this function is continuous because it's just a polynomial minus x. For x positive, the function is continuous because it's just a polynomial. F of x is equal to x. Okay, and actually, this function is continuous at 0, infinity, and minus infinity, 0. 0 always included. Okay, so it's continuous everywhere. Okay, because at 0 it's left continuous and right continuous because it's just a polynomial. Okay. Okay, so this function is continuous for all x. Now, if you look, for instance, at power functions, okay, we know that the inverse root functions. Okay. Now, how to show that root functions are continuous on their domain. Okay. Now, this doesn't follow from our limit laws. Okay. So we need here some general result. Okay, about the relationship whether an inverse function is still continuous whenever a function is continuous. Okay. Now, actually, this result really holds. Okay. So if f is continuous, then the inverse function is continuous as well. Okay, I'm not going to prove this. It's not so hard to prove, but just to give a general reason why this is true here is we know you obtain the inverse the graph of the inverse function by reflecting about the line y is equal to x. Okay. Now, if you use the primitive definition of continuous, namely you can draw the graph without lifting your pencil. Okay. This will certainly be preserved if you reflect the function about the line y is equal to x. Okay, so something like this will certainly hold. You can also prove it in a more rigorous sense. Okay. Now, from this, this is already helpful because this tells us, okay, that also all root functions are continuous. Now, how about trigonometric functions? Okay. For trigonometric functions, we haven't given a good definition in this lecture, so we use the primitive definition you have learned in school. Namely, you look at the unit circle, and you measure here the angle in so-called radiant measure, and then you see here the cosine of x, and you see here the sine of x. Okay, so this is the primitive definition you have learned in school, okay, in high school. And from this primitive definition, because the angle here is changing continuously, okay, so the graph which is generated by this process here, okay, will be continuous, okay. So from this primitive reason, okay, you see that sine of x and cosine of x are continuous. Now for the tangent, you can already argue more rigorously. Namely, you know that the tangent of x is the sine of x over the cosine of x. Okay, so since you know that sine of x is continuous, and this function is continuous, so this will be continuous as well, except if the denominator is equal to 0, where the function is not defined. So this function is continuous at for all x except x is equal to 2k plus 1 times pi half. Okay. And then you use again this fact here. So from this fact, you see that the inverse sine function, inverse cosine function, inverse tangent function all are continuous. Okay. So everything is continuous. Now we have the final set of functions which are left are exponential functions. So if we look at f of x is equal to e to the x, why is this function continuous? Actually, for this function, it's a little bit hard to argue for us because we haven't defined it precisely. But if you remember, we defined the problem which we had was defining this function when x is an irrational number. And here we looked at the graph. We saw it's kind of dotted, and we filled holes such that the graph keeps being increasing. Okay. Now, from this definition, okay, kind of, this is not really a definition, okay, but from this definition, you see, okay, by the very definition of the function which we used, this function is continuous. You see that kind of here we are running into many problems because sine x and cosine x, we have never defined them really in a precise sense, okay? So actually, if we want to really prove that those functions are continuous, we have to use the definition, okay? But this is a little bit hard to argue if you have such a definition, okay? This problem, everything is coming from high school, okay? Because in high school, you have never defined this function properly, okay? You argue what the function is, okay? But this is not a real definition. Now, for this function, the problem is even, we have even this kind of we can understand, okay? But for this function, again, because we haven't defined it, okay? But from the definition, we can argue that this function is continuous, okay? This shouldn't be very satisfactory, and later on we will prove this precisely, okay? We will precisely prove that this function is continuous, but much later, maybe in 1 month or 1.5 months. Now, since we know that this function is continuous, you can again use the result that the inverse function is continuous as well, and then you get that the logarithm, the natural logarithm, is continuous on the domain. And of course, the same is true for all other exponential functions, all other logarithmic functions. All other logarithmic functions, as we have seen, just differ by constants. So they are all. Once you know that this one is continuous, all other will be continuous. And the same is true if you choose here any other base instead of e. Okay. So actually, many functions are continuous. Polynomials are continuous. Rational functions are continuous. Root functions are continuous. Trigonometric functions are continuous. Inverse trigonometric functions are continuous. Exponential functions are continuous, and logarithmic functions are continuous. Okay. So in our textbook, this is summarized as one theorem that all those functions are continuous. I'm not going to write this on the blackboard. Now, so this helps you already to, if you have even more complicated functions like h of x is equal to sine x plus e to the x over x plus 1. Okay. Now, to figure out that such a function is continuous is getting now quite easy because we know the sine continuous everywhere, e to the x continuous everywhere, the sum of continuous functions is continuous, x plus 1 continuous everywhere, and the quotient is continuous whenever the, except for the points where the denominator is equal to 0, so only the point x is equal to -1 is a problem here, okay? So from this theorem from our textbook, okay, we see that this function is continuous for all x in R except, actually, I shouldn't write this like this. I write for all x in R without -1. Okay, and but the important thing is the way we argue, okay? Because we have already figured out for certain functions that they are continuous, and we know certain building rules, okay? That's why we can also easily figure out that such a function is continuous. Now, except addition, subtraction, multiplication, and division, there is another fundamental operation for functions, namely composite functions. Okay, so composite functions. Okay, so just to remind you, we normally write this like f ring g of x, and the meaning of this is that we plug g of x into f of x. Okay, this is a composite function. So our question is, will such an operation also preserve the property of being continuous? So if g of x is continuous, okay, at some point a, and f is continuous at g of a, will the composite function be continuous as well? Okay, we would like to have such a theorem. Then we would have another rule, okay, for composing functions, okay, which preserves continuous. Now, this in fact is is true. So in our textbook, first the author calls this a theorem is proved, which already points in this direction, namely if the limit of g of x as x tends to a is equal to b, so existent is equal to b, and f is continuous at b, then the composite function, I shouldn't write it like this. Then the limit of f of g of x as x tends to a is equal to f of b. Okay, so this theorem is easy to prove using the epsilon delta definition of the limit. You can try this as an exercise. Okay, try to prove using the epsilon delta definition that this theorem here holds. So for an epsilon, given epsilon, try to find the delta such that if x is sufficiently close to a, this function here, this value is sufficiently close to f of b. It's not complicated for this situation. But this is a very useful property because you can rewrite this as the limit f of g of x as x tends to a is equal to, if we plug in for b here this relation, you see this this gets a very nice form, and you know this also from high school. So if you have a continuous function f, you have a look at the composite function, you take a limit, you can take the limit inside, okay, because the function is continuous. Okay, this rule more or less tells you that you can take the limit inside. Okay, so we saw already that f of x is equal to the nth root of x is continuous. Okay, so we see from this that the limit of the nth root of x as x tends to a is equal to g of x is equal to the nth root of the limit of g of x as x tends to a. Okay, and actually this was one of our limit laws, okay, which we haven't proved till yet. Okay, so this is the proof here. Of course, you need assumptions here. In case where n is even, this number should not be smaller than 0. Now, this property is sometimes very helpful. I have a very easy example. Okay, so for instance, if you have something like this here, because we know that inverse trigonometric functions are continuous, so you can write this as the inverse sine of the limit as x tends to 1, x minus 1 over x squared minus 1. So because the inverse trigonometric function is continuous, you can take in the limit. Okay. Now, this limit, we have computed this already many times, is 1/2. So the answer is pi over 4. Okay, so you see already how to apply this using such an easy example. And another important application is that this implies that continuous functions, the composite function of continuous functions are continuous. The composite function is continuous. Okay, because if you want to see a proof, okay, so let's say we have two functions, f of x and g of x. Now, let's assume that g of x is continuous at a and f of x is continuous at g of a. Then if we look at the limit as x tends to a of f of g of x, okay, so because this function is continuous, so we can take in the limit. But this function is continuous as well, so this limit we can easily evaluate as g of a. So what we get is f of g of a. Okay, and that's already the proof. So from here we already see that the composite function is continuous as well. Okay. So this is another convenient property. So if you have a complicated composite function, okay, you can use this in order to figure out where the function is continuous. Of course, the domain has to domain and range of the functions have to match. Okay, so if you look at a very, very easy example, for instance, you have the function f of x is equal to the inverse sine of x squared. It doesn't matter, but let's stick to my x squared minus 1. Okay. Now you see already the inverse trigonometric functions are continuous. Polynomials are continuous. Okay, so the composite function of continuous functions will preserve this property, so it's continuous as well. The only thing which you still have to figure out is the range. Okay, but this, also in this case it's very easy. Okay, but actually this function will be continuous. For all x in the domain. Okay, because I have to. So let's discuss the last thing which I want to discuss about continuous functions is a very important theorem which looks very innocent, which looks like a result which is trivial, but which captures a very important property of continuous functions. And this theorem is called the intermediate value theorem. Okay. Okay, so I maybe just first start by stating the theorem. So the intermediate value theorem. Okay, so let f be a continuous function on a closed interval AB, then let's say m is a value between f of a and f of b. Then there exists a C inside the open interval AB such that f of C is equal to m. Now this really looks like a trivial result. Maybe let's first plot a graph to understand the result. Let's say this is A here, this is B. Of course, this f of A and f of B might be reversed. Okay, it might be that f of A is larger than f of B. Okay, so it might be reversed. But let's maybe just stick to this situation. So maybe you have something like this here. Okay, so now what you do is you choose a m, okay, which is somehow, let's say, for instance, this one. So this is your m. Now, what the result claims is that there is a corresponding c, and actually you can see it here. this c here, okay, such that f of c, the function value of c, is just equal to n, is mapped onto n. Okay. Now, this is something which you expect from a continuous function. Okay, and in some sense, this tells you that a continuous, because if you look at the definition which we gave, namely the limit of f of x as x tends to x0 is equal to f of x0, from this definition, okay, you cannot really see why a continuous function has the property that if you plot the graph, okay, that you can draw it without lifting your pencil. Okay, from our definition, from our actual definition, okay, you cannot really see this. Okay, but this here tells you, okay, that actually a continuous function has this property, namely that all values, once you have a continuous function on the interval, all values between f of a and f of b have to be taken on, okay, by the continuous function. Now, as I said, this result, okay, is kind of, if you see this for the first time, it looks like a trivial result. Okay, the reason is because in high school you have learned that the continuous function, or someone told you that the continuous function is a function where you can plot the graph without lifting your pencil. Okay, but actually this theorem kind of tells you that this is true, starting from our new definition. Okay, now we are not able to prove this theorem. This is too complicated. Okay, if we want to prove this theorem, we should have to look at things in much more details. Okay, you prove this normally in classes on real analysis or something like this. Okay, so for us it's more important what are the consequences of of this result. Okay, as I said already, the main consequence is that you can think about the continuous function as a function where you can plot the graph without lifting your pencil, kind of. Okay, because of this result here. Another important consequence, which you maybe have already seen in high school, is this gives you actually a method for finding roots of functions. Okay, so for instance, if you are interested to find a number, okay, so if you have the general question, does there exist a number such that the cube of the number is equal to 1 plus the number? Okay, so is there a number such that the cube of the number is equal to 1 plus the number? Okay, so the question is whether this equation has a solution. Now, you define a function f of x is equal to x to the cube minus x minus 1. Okay, so you see, this is a polynomial, so we know this function is continuous. Okay, now you plug in f of 0. So you see f of 0 is equal to minus 1, smaller than 0. Okay, and you plug in f of 2. Okay, so f of 2 is 865, which is larger than 0. And now, because this function is continuous, okay, on this interval, we see, okay, if we choose a value, okay, between minus 1 and 5, for instance, 0, okay, this result tells us there must exist a c such that f of c is equal to 0. So in other words, from the mean value theorem, we get that this polynomial has a root between 0 and 2. Okay. Okay. So this is a theoretical, this is what we call in mathematics existence result. Okay. It tells you such a C must exist, okay, but it doesn't tell you how to get it, okay, which would be, if this result also would tell us how to get it, would be much better for this situation, okay. It is not possible, okay, but we see that using the intermediate value theorem, we can easily argue for this case that there must be a root between 0 and 2, and we can kind of improve this. Okay, you choose now the point 1. Okay, you look, is the function at the point 1 larger or smaller than 0? Okay, and if the function is at point 1, so if you plug in 1, you see it's minus 1. Okay, so you know actually the root has to be between 1 and 2, and you go on like this. Okay, so you always choose the middle of the interval. And then you evaluate the function at this middle point, and then you drop either the upper half or the lower half of the interval. And like this, you get a method, okay, how to find roots of this polynomial, a general method, which you maybe have heard in high school. So this is one application of the intermediate value theorem. Okay, actually the graphing devices are using this result in order to plot functions. A graphing device will always assume that the function is continuous. Okay, so a graphing device will just evaluate the function at some points and then connect the points by a line. Okay, that's why every graphing device, so kind of the graphing device is using this theorem. Okay, in order to plot functions. That's why every graphing device will have big problems to plot functions which are not continuous. Okay. Now, this is another application. We look at the final example. The final example is coming from a midterm exam from last year. Okay, so this is the example which I had in my midterm last year. Okay, now you have the following situation. Okay, here is Taiwan. Okay, here is my country, Austria. Okay. Now every year I'm flying from Taiwan to Austria. So, okay, here's Taipei. Here's the capital of Austria, Vienna. Okay, and I'm flying from Taiwan to Austria. Okay. Now, assume that the time it will take to go there is roughly maybe 12.5 hours. Okay. Now, assume we make some assumptions. Assume that the plane is so I'm first flying to Austria, and then a week later I fly back to Taiwan. Okay. Now, assume that the route which the plane is taking is exactly the same. Okay, in both directions. Okay. Also assume that let's say on Monday I start at 9 o'clock. Okay, flying to Austria, and 1 week afterwards I start at 9 o'clock in Austria and fly back. Okay, to Taiwan. Now use the intermediate value theorem to prove that there exists a time point where the plane passes the same point. Okay, on the way to Austria and then the way from Austria to Taipei. You understand what I want you to do? Okay, so proof. Use the intermediate. I abbreviate intermediate value theorem by intermediate value theorem to show that there exists a time point let's say t0 at which the plane passes by the same point. Okay, of course the plane, if you go from Taiwan to Austria, okay, the plane will have maybe a different speed, okay? And if you go then from Austria back to Taiwan, it will be different, okay? The time is the same, okay, because we start here at 9 in the morning, okay, and we are at 21.5 in Austria, okay, and the same on the way back, okay. We start at 9 here and at the same time in Taiwan, okay. Now what you should prove is that there is a point, okay, a time point where we are on the way there and on the way back we are at the same place. No matter how the plane is flying, okay, because maybe the plane is flying very quick at the beginning and then very slow, okay. And on the way back, maybe it's different. Maybe it's a constant velocity all the time to Taiwan. But still, there is one time point. Okay, so maybe at 12 o'clock, you are at the same place. Okay, but of course, your direction is different. Now use the intermediate value theorem to prove this. Is it clear? Is the problem setting clear? You do not have to take into account that there are 6 hours time difference. Okay? You do not have to care about this. Because actually there are 6 to 7 hours time difference. You do not have to care about this. Time is measured absolutely. Okay? And you start at the same. You start at the same time here, 9 o'clock in the morning. And you are in the evening then in Austria. And you start here at 9 o'clock in the morning, and you are in the evening in Taiwan. It's the same time. The same time span. Of course, you can plot the graph first, but then you have to keep in mind that the intermediate value theorem does not use a picture. So first, in order to solve this, first plot the graph. Okay, from a graph you see this is quite obvious, and then translate it. Then translate it into the language of the intermediate value theorem. So, which means you have to tell me what is the function, okay, and how to apply the intermediate value theorem to this function. Or maybe just tell us what is the idea. So I maybe plot first this picture you have here. So something like this should be okay. So here is the start point. So here's kind of 9 a.m. and here will be the end point. So 12.45 hours later. So okay. Now, you see, first I have to explain what are the two functions. Now, this actually what I plot here is that this function, okay, I'm flying to Austria. So what I see here is the distance to Taiwan, okay. So at the beginning the distance is 0, and at the end the distance is the distance from Taiwan to Austria, okay. So this is the first function, f of x, which is the distance, you can say from Taiwan because you are leaving Taiwan. Okay, and you have another function, g of x, which is now the other direction. Okay, but in the other direction, of course, your important point is always Taiwan. Okay, so it's the distance to Taiwan. Okay, so g of x is the distance to Taiwan. Because at time point 0 or at 9 a.m., okay, the distance is just this distance here, okay, because you are starting to fly to Taiwan. And then the distance is getting smaller and smaller, okay. And of course, from this picture you see, okay, there is a time point here, okay, where at the same time, okay, we are at the same place, okay, because the distance from Taiwan and the distance to Taiwan is the same. Now, which function do you have to use in order to apply that? This does not use the intermediate value theorem, and it relies on a picture, so it proves nothing. Okay. So what is the function? You know it? Which function? On which function do I have to apply the intermediate value theorem? Who knows it? Which function? So we define a new function, f of x. But I want to define a function in terms of these two here. Right, yeah, you take f of x and you subtract g of x. Okay. Now, this function, of course, you have to assume that this function is continuous on this interval here. Okay, you can assume this because unless you stop somewhere, actually you stop in Bangkok, but we do not take this into account. Okay, so we say, okay, you do not stop. So now you see that if you look at f of 0 or f of 9 p.m. Okay, at this point here. So you see that because this function is 0, but this function is the distance between Taiwan and Austria. So this is negative. Okay, and you see that f at the end point, so 9:30 in the evening, now you see at this point here, okay, now f of x is the distance and g of x is 0, so it's larger than 0. Okay, so you see that because 0 will be a point in the interval f of 9 a.m. and f of 9:30 in the evening. Okay, so now you can apply the intermediate value theorem. So there exists a t0 such that f of t0 will be equal to 0. Okay, but if you look at this here, this tells you that f of t0 is equal to g of t0. So the distance is the same. So you're at the same point. Okay. So you see, actually, this exercise last year, not so many students could solve it, but actually it's quite easy because you can immediately come up with this picture here, okay? And then the remaining thing is just to translate this picture into the language of the intermediate value theorem, which means you have to find the right function on which you want to apply the intermediate value theorem. Any questions? Of course, this example will not appear this year in the midterm. Okay, so if there are no questions, then we stop here and we will go on Monday.